Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Master's Degree Programs. Master of Science, Renewable Energy and Environment, MSCRWEE. Semester I. MRW 001 Energy Conversion. Block-1 Basic Concepts of Energy Conversion. Unit-2 Combustion Principles and their Applications. 2.1 Introduction. Combustion is a process by which the chemical energy of the fuel contained in it as internal energy is converted into heat energy. Combustion consists of process causing chemical reaction between the combustible part of the fuel and oxygen with a view to generate heat. The products formed as a result of the process are carbon dioxide, carbon monoxide and water vapor. Carbon dioxide is a result of complete combustion of carbon, whereas carbon monoxide is a result of incomplete combustion and compared to carbon dioxide contains only half the amount of oxygen of per unit weight of carbon. The oxygen of combustion is supplied from air, which from combustion considerations contains 20.9% of oxygen and 79.1% of nitrogen by volume. An ideal combustion aims at producing maximum amount of heat by burning fuel and also in utilizing as much as possible of waste heat resulting from combustion. Flue gas, which comes out through stack after combustion, contains besides carbon dioxide, water vapor, compounds of nitrogen and compounds of sulfur such as sulfur dioxide and sulfur trioxide. To illustrate the importance of fuel combustion, let us cast a glance at the chart shown in Figure 2.1, which shows the application of the combustion of fuel when it serves our domestic purposes, and thereafter when it is used for industrial purposes, within dries, heating and heat treatment furnaces, metallurgical furnaces, power generation plants, etc. Objectives. After studying of this unit, you should be able to understand the fundamentals of the combustion principles, the characteristics of the various combustion processes, and the application of combustion principles to different types of fuels. 2.2 Chemistry of combustion processes. Fuels, solid, liquid and gas, release their stored chemical energy during combustion. Stoichiometric combustion of a fuel is defined as the process of complete combustion with evolution of heat. The prerequisite of any such phenomenon is the availability of the fuel in gaseous state, where it can mix with oxygen in the surrounding air, and the prevailing temperatures to be high enough so that combustion reaction takes place, leading to release of heat energy. In the case of liquid fuels, the condition of continuous supply of vaporized fuel is met by the vaporization from the surface of the fuel due to heat transfer to the surface from the flame itself. In case of coal, release of volatiles after ignition fulfills this role. In the case broadly defined as the chemical breakdown of the original wood constituents under the of fuels like wood, this is achieved through the phenomenon of pyrolysis that may be broadly defined as the chemical breakdown of the original wood constituents under the influence of heat, leading to the formation of combustible volatiles and chars responsible for flaming. 2.2.1 Calorific value of a fuel. The calorific value or heat of combustion or heating value of a sample of fuel is defined as the amount of heat evolved when a unit weight or volume in the case of gaseous fuels of the fuel is completely burnt and the products of combustion cooled to standard temperature of 298 Kelvin. We usually encounter two kinds of calorific values. One is referred as gross calorific value or higher heating value, HHV, and other is called net calorific value or lower heating value, LHV. Gross calorific value, GCV, It is the heat released when unit mass of coal is burned completely at constant volume in saturated oxygen under pressure of 25 to 30 bars, the original and final products being at 25 degrees Celsius. Net calorific value, NCV. The net calorific value or lower heat of combustion is derived from the gross calorific value by deducting the latent heat of vaporization of water present and formed. Thus, NCV, mjkg, is equal to GCV, mjkg, 0.22% H. 2.1. The heat of combustion may be calculated approximately by proximate ultimate analysis and is given by NCV is equal to GCV, 2.45, 9 mH plus MMW plus HW. 2.2. Where mH is equal to percentage of hydrogen, MMW is equal to percentage of external moisture, and HW is equal to sensible heat of water between 25 degrees Celsius and 100 degrees Celsius in mJ. This is also called the calorific value on wet basis or as received basis. 2.2 chemical reactions of combustion. Chemical reactions may be classified into exothermic and endothermic i.e. the reactions can proceed with the development of heat or with its adsorption, respectively. All combustion reactions develop heat but in reverse reaction of dissociation of product of combustion, the adsorption of heat takes place. The equations of some of the important combustion reactions are given below. 1. H2 plus 1 by 2 O2 is equal to H2O, VAP, plus 57,810 kilocalories mole. 2. H2 plus 1 by 2 O2 is equal to H2O, liq, plus 68,360 kilocalories mole. 3. C plus 1 by 2 O2 is equal to Co plus 29,430 kilocalories mole. 4. Co plus 1 by 2 O2 is equal to Co2 plus 68,220 kilocalories mole. 5. C plus O2 is equal to Co2 plus 97,650 kilocalories mole. 6. Co2 plus C is equal to Co, 38,790 kilocalories mole. 7. C plus H2O is equal to Co plus H2, 28,380 kilocalories mole. 8. CH4 plus 2O2 is equal to Co2 plus 2H2O plus 192,400 kilocalories mole. 9. C2H2 plus 3O2 is equal to Co2 plus 2H2O plus 3,45,800 kilocalories mole. 10. H2S plus 3 by 2 O2 is equal to H2O plus SO2 plus 124,850 kilocalories mole. 11. S plus O2 is equal to SO2 plus 69,800 kilocalories mole. 2.2.3 Combustion efficiency. Combustion efficiency can be given as energy released from the fuel after combustion upon energy contained in the fuel before combustion. The combustion efficiency decreases with the following factors. I. Incomplete combustion. 2. Combustion losses. 3. Partially oxidized hydrocarbons or unburnt carbon particles. 4. Absence of excess air. The combustion efficiency is optimized when proper mixing of fuel and air is supplied as to minimize combustion losses associated with excess fuel and excess air. 2.2.4 Fuel-air ratio. Fuel-air ratio is an important parameter to be considered as the reference condition for combustion process. It depends on the CH ratio of the fuel. The expression for stoichiometric fuel-air ratio is given by F-A ration is equal to 0.0874, 1 plus HC ratio upon 1 plus 3 HC ratio .4. I. For hydrocarbon with general formulas CnHn, the stoichiometric FA ratio is 0.0677. 2. For pure carbon, FR ratio is 0.0867. 3. For petroleum fuel like benzene and methane, the FR ratios are 0.0754 and 0.0580 respectively. 2.5 air required for combustion. For most efficient use of fuels, its complete combustion is essential so that all heat which it is capable of giving for external use is available. In practice, several factors affect the combustion process, and it is found that the complete combustion cannot result unless more than the theoretical amount of air is used. However, the unavoidable consequence of using excess air is a loss of sensible heat necessary to heat this air to the temperature of flue gases. And this reduces the gain due to the use of excess air to some extent. 2.2.6 Analysis of the combustion products. The analysis of the combustion products of fuel helps in studying the actual combustion process in a furnace and of its effectiveness. The loss of heat in flue gases, the amount of excess air required, and infiltration of air into the furnace, etc., can be determined through gas analysis. The analysis of the exit gas from the chimney for most engineering purposes involves determination of N and O, the important being CO. The apparatus commonly used for analysis of the products of combustion is SOET apparatus. This device determines directly the fraction by volume of CO and O in the gas. If the combustion is incomplete, gases will contain CO if excess air is used. There would be a content of O2 in the gas. As absence of both O2 and CO would indicate theoretically that the combustion is just complete with no excess air. An appearance of both combustible matter and free O in the flue gases would indicate the ineffectiveness of combustion in spite of supply enough air. This may result due to inadequate mixing up of fuel and air throughout the combustion of gases, air infiltration, etc. May also cause incomplete combustion of reactions in the furnaces. 2.3 Combustion processes. The phenomena of combustion may be considered in the chemical and technical aspects. The chemical aspect of combustion of carbon in the furnace of a steam generator considered to occur in two stages. In first stage, the volatile matter of the fuel is released in the form of gaseous hydrocarbons, and this matter burns in gas phase. The reaction is rapid, and for completion of reaction, adequate supply of air and turbulent mixing up of air and combustion gases are necessary, otherwise smoke formation results. The specific combustion rate of a particle of fuel in suspension in air steam depends upon its size, the surface of the contact with air, and upon its velocity relative to that of air. A small particle of fuel would have large specific surface contact but small relative velocity with respect to air. It will have a higher combustion rate than that of large pieces of fuel. Technically, the combustion process depends on the geometry of the fuel bed. And beside the fuel size, the rate of firing, the supply of primary air and moisture content in the fuel also greatly affect the combustion process. In the case of pulverized fuel, the aerodynamics of the furnace chamber is the most important factor that controls the efficiency of the combustion process. The design of the burners, i.e., whether producing long flame or turbulent short flames, their orientation in the furnace chamber, combustion space requirement, etc., are some of the important aspects in this aerodynamic requirement. There are mainly three types of combustion processes which will be described in the following sections. 2.3.1 Flameless process of combustion. Flameless combustion is also called catalytic combustion. The process of Flameless combustion produces immense economy in fuel consumption with the added facility of ideal conditions of cleanness in the working conditions in the workshop, which is very easy to maintain. This circumstance, in the first instance, leads a considerable improvement in working conditions, while at same time preserving valuable installation and equipment from rapid soiling and premature wear. Essence of the process of flameless combustion. The principal factor in this process is the presence of catalyst or material capable of considerable accelerating the combustion reaction when the fuel is brought into contact with its surface. The phenomena can be explained by the fact that the surfaces of the different materials at low temperatures have different degrees of activation. For example, platinum, ferroxides, nickel, and vanadium are known to endowed with catalytic properties at low temperatures. At high temperature, the surfaces of all material exhibit catalytic properties, thus all refractory material can be considered to be catalyst. Some of the important refractory materials which have such property are chamote, fireclay, dinas, magnesite, alundum, etc. The cause of the catalytic properties of certain materials at low temperatures lies in all probability in their capacity to absorb and to concentrate fuel gas on their surfaces. The catalytic properties of the materials at high temperatures may be explained by the presence of considerable quantities of radiant energy, as well as by the emission of electron on the incandescent surface of the catalyst. High velocity of combustion of a fuel gas mixture per unit volume of combustion chamber of tunnel creates a high temperature, thus increasing the capacity of furnace. In the practical field, the process of flameless combustion is obtained in the following manner. The combustible air-gas mixture is directed to a channel or tunnel. A complete combustion of gas-air mixture comes into contact with combustion chamber made in the wall of the furnace. In this combustion chamber refractory surface of the tunnel, which plays the part of a catalyst. At the start, when the wall of the tunnel are cold, the air-gas mixture is ignited on entering the tunnel with the help of some outside source, such as a match, electric spark, etc., following which the usual combustion or combustion with flame takes place on the cold wall of the tunnel. The process continues till the walls heated to a temperature capable of maintaining combustion, whereupon the flame disappears, and the combustion continues without flame, but considerable increases of temperature. 2.3. To submerged combustion process. Submerged combustion refers to the combustion of fuel inside the liquid medium. When a liquid or gaseous fuel is introduced in a liquid medium to heat directly, difficult combustion can be achieved at the condition that the pressure of fuel entering this seemingly liquid medium is to be higher than the counter pressure offered by the medium. Also, at the time of its entering the medium, the stream of fuel must be semi-pulverized or divided into sufficient number of tiny streams, each of which produces a bubble of products of combustion so that the hot surface of the bubbles communicates their heat to the surrounding medium. The larger the number of the bubbles, the quicker the transfer of heat to each and every part of the surrounding medium. On the other hand, the larger the number of separate streams and the smaller streams, the higher is the pressure offered to the natural tendency of the surrounding liquid to force its way inside the burner itself. Practical application. It was undoubtedly the chemical industry that derived highest advantages from submerged combustion process, especially in such processes as combustion of solid, evaporation of solutions, galvanization, heating of solutions, etc. For example, Before submerged combustion process, it was necessary, in order to heat any solution, either to allow superheated stream to pass through it or place a stream coil inside the solution. In the first instance, the concentration of solution was inevitably affected and the solution got weaker. In the second instance, the premature destruction of the coal, due to oxidation, frequently took place. Submerged combustion offers the remedy for both above drawbacks, appearing to be an ideal process. Remarkable success is observed in application of submerged combustion process for heating such solution as calcium carbonate, sodium carbonate, etc., where the reduction concentration is highly undesirable. In the process of dyeing, again, it is of considerable importance that the temperature of the dyeing chamber should not be allowed to rise above a certain level, after which the material under dyeing is in danger of getting boiled into a formless mass. Of no less important is the application of submerged combustion in galvanizing baths, where it is undesirable to allow the solution of the bath to get gradually liquefied. 2.3.3 Diffusion combustion process. Diffusion combustion is the oldest process of combustion. It was known to the people of the ancient world. A primitive wick lamp was used from the time immemorial, and it is exactly in this primitive lamp, or in a modern wax candle, that a true diffusion combustion takes place, with the slow and uniform mixing of fuel with air, by way of diffusion, throughout the process of combustion. The diffusion combustion may be achieved with the use of two types of burners, cylindrical and flat burners. Here it will be of interest to consider the main factors in both the cases related to the length of the flame, i.e., the velocities of flow of air and gas, coefficient of diffusion, change of dimensions of burners, etc. The expressions for the length of the flame for cylindrical and flat burners are as follows. Cylindrical flame H half infinity V upon K into R square, or H is equal to K1 V upon KR square. 2.5. Where H is equal to height of the flame, m. V is equal to velocity of the air and gas flow, m sec. K is equal to coefficient of diffusion. K is equal to proportionality constant, and R is equal to radius of the inner cylinder. Flat flame H half infinity V upon Ka square, or H is equal to K to V upon Ka square, dot to dot 6, where K2 is equal to proportionality constant, and A is equal to thickness of the gas stream. 2.4 Application of combustion principle to solid fuels. Naturally occurring solid fuels include wood and varieties of coals, while prepared ones include coke, charcoal, briquetted and pulverized solid fuels. Let us discuss some of the important combustion systems which make use of solid fuels. 2.4.1 Combustion of solid fuels in domestic ovens. Solid fuels like wood, coal, bagasse, etc. are used in various types of ovens for cooking, heating rooms, and production of hot water. Though domestic ovens making use of solid fuels are being used from the primitive age, several types of energy-efficient woodcook and coal-burning stoves have been developed to save not only energy but also to control environmental pollution. 2.4.2 Combustion of coal in furnaces for steam generation. There are several applications of steam by making use of heat produced by the combustion of coal. The power of steam is utilized for different purposes. For example, industrial boilers are used to supply steam for various industrial processes. 2. Locomotives use steam engines to drive mechanical loads. 3. Steam turbines are used in thermal power plant to generate electrical power. For the above cases, a large amount of coal is burned to generate heat energy. 2.4.3 Combustion calculations for solid fuels. For combustion calculations in respect of solid fuels, we shall discuss some examples for the determination of the following factors. I. Theoretical quantity of air required for complete combustion. 2. Volume of products of combustion. And 3. Calorific value of fuel. 2.5. Application of combustion principle to liquid fuels. The most common liquid fuels are natural petroleum, crude oil, gasoline, manufactured or artificial tar oil, coal tar, shale oil, molasses, etc. Oil is used for domestic purposes, running automobiles, and also used in furnaces to generate steam. Oil has several advantages as a fuel. These may be summarized below. I. Low excess air is used so combustion losses are less. 2. It is possible to build high-capacity plants burning oils. 3. Storage space required is small and handling is easy. 4. Ash and refuse are small, so handling costs are nominal. It does not deteriorate easily, so banking losses and standby losses are small. However, the great disadvantages of the liquid fuels is that the heat produced is costly as compared with coal or gas. Moreover, in a country like India, where natural resource like oil is scant, the application of oil for power generation is limited. For burning of oils, several types of burners are used. The purpose of an oil burner is to atomize or vaporize the oil completely to produce a jet of suitable shape for best mixing with air so as to give complete combustions with minimum of excess air. Oil burners may be principally classified as vaporizing and atomizing. Vaporizing burners used in industrial and domestic applications such as blow torches or portable gasoline moves and depend for their action a wick or hot fuel line for vaporization. There is hardly any application of these burner in steam generation since the heavy oil used is not capable of easy vaporization. Atomizing burners are commonly used for oil-fired furnaces of steam generators. A thorough mixture of oil with air is essential for complete combustion of fuel. This mixing can be achieved by dividing the oil, as it is fed into furnace, into fine globules to bring in it immediate contact with combustion air. The atomization of fuel is achieved in different ways in different burners, two common methods being steam or air jet atomization and mechanical atomization. The combustion efficiency of the burner depends on the one of the important factor, i.e., the size of the oil particle after atomization. According to the Heat Engineering Research Institute, Moscow, the maximum radius of particles can be found from the following equations. A. For steam or air atomizer, R is equal to 1375 upon Pc square. 2.7. Where ρ is the density of the surrounding medium in m cube. kg, atomizing agent. C is the relative velocity of all particle and atomizing agent. B. For mechanical atomizer, R is equal to 7.8 upon P dot to dot 8, where P is the oil pressure in atmosphere, ATM. 2.5.1 Direct combustion of all fuels. This is the simplest and so to say primitive method of fuel oil combustion. It is employed for burning small quantities of fuel. For example, kerosene oil is generally used in rural areas for cooking and lighting. Kerosene stoves and lamps respectively are used for the same. For heating of room, oil is burnt in a Combustion chamber. But application of oil for room heating is rare. 2.5.2 Combustion of liquid fuels in I.C. engines. The main differences among the different types of internal combustion engines are in respect of the kind of fuel used, the manner in which the fuel and air are introduced in the engine cylinders, and the manner of igniting the charge. Internal combustion engines may be spark ignition or compression ignition types and may work on 4-stroke or 2-stroke cycle principle. Diesel engines using high-speed diesel fuels working on the compression ignition principle and on 2-stroke or 4-stroke cycle are used where high capacity plants are needed. Most of the automobiles like car, truck, buses, etc. are run by using diesel fuels. Diesel locomotives are used in railway transportation system. Automobiles making use of petrol are fuel efficient and causes very less pollution for environment. In diesel engine power plant, a large amount of diesel fuel is utilized to drive generator by diesel engine to generate electrical power. But the application of diesel oil for generation of electrical power is limited. 2.5.3 Combustion calculations for liquid fuels. Like solid fuel, we shall discuss the following calculations for liquid oil fuel. These are: I. Determination of total air requires for complete combustion. 2. Quantity of the products of combustion. 3. Calorific value of oil. 2.6 Application of combustion principle. 2. Gaseous fuels. Gaseous fuels can be broadly divided into natural gas and manufactured gas. Natural gas may be considered as the associate product of petroleum which exists naturally under the surface of the earth. Some natural gas is also associated with coal. Natural gas comes of gas wells and petroleum wells and contains 60 to 95% methane with small amount of other hydrocarbons such as ethane, naphthene, carbon dioxide, carbon monoxide, nitrogen, etc. Manufactured gases are obtained from solid and liquid fuels. The principal manufactured gases include blast furnace gas, producer gas, coke oven gas, water gas, liquefied petroleum gas, biogas, etc. For combustion of gaseous fuels, various types of burners are used. The burners can be classified mainly into two groups on the basis of the formation of gas-air mixture as follows. A. Burners in which gas-air mixture is prepared prior to combustion. These are high-pressure injection burners in which gas injects air from the surrounding atmosphere. These burners may have single-stage suction or multistage suction. B. Burners in which gas-air mixture forms in course of process of combustion. These are I. Diffusion burners, 2. Irregular turbulent burners, and 3. Submerged combustion burners. Some of the important systems where gaseous fuels are burnt using above principles are discussed in the following two subsections. 2.6. 1. Combustion of cooking gas. Liquefied petroleum gas, LPG, and biogas are two manufactured gases which are used for cooking, production of hot water, etc. LPG is widely used in all over the world for cooking. LPG is obtained by liquefying petroleum gas at a very high pressure in a cylinder or a container. When it is released for combustion in air, then due to drop in pressure, it converted into gaseous fuel. Several types of LPG burners are used for burning this gas for cooking. Biogas is obtained by anaerobic digestion of biomass. Most important raw material used production of biogas is cow dung. It is an environment-friendly Energy resource which does not produce smoke and ash during burning. So it helps in environment pollution control. Biogas is generally used for cooking, production of hot water and lighting. Biogas burners control are slightly different from LPG burners. 2.6.2 Combustion of gaseous fuel in gas turbine power plant. Gas turbine power plant makes use of energy of gaseous fuels to generate electrical power. Here, gas turbine is the prime mover which drives the generator. As compared to reciprocating IC engines, gas turbines have higher mechanical efficiency due to fewer sliding paths in construction. While the adiabatic expansion of gases in the cylinders of the IC engines is incomplete, the gas turbine allows for a more or less complete expansion of gases which increases plant output. Gas turbine, being a rotating machine, is well balanced at all speeds. 2.6.3 Combustion calculations for gaseous fuels. In this subsection, like other fuels, we shall discuss the methods of combustion calculations of gaseous fuel with example. 2.7 Summary. Chemical reaction of combustion can be classified as exothermic and endothermic. Flameless, submerged and diffusion are three basic modes of combustion processes. The most important factor at optimizing combustion is to ensure that the proper mixture of fuel and air is supplied to combustion process. The analysis of combustion products of the fuels helps in studying the actual combustion process and its effectiveness. For power generation, solid fuels are used widely than other fuels. Thank you. Subscribe to our channel for more updates.